Hey everyone, in this video I will be discussing how to solve a high order linear ordinary differential equation. Ordinary meaning we have only one independent variable. Differential equation means we have the derivatives of that unknown function, and homogeneous means we have zero in the right hand side, meaning there is no term without y or its derivatives in the equation. And the constant coefficients means all of these coefficients, in this case 1, a1 up to an, they are all constant numbers. To solve this differential equation, the first step is to form the characteristic polynomials, meaning you're going to have 1 times variable, maybe I use r. R is what we would like to find, to the power of n, plus a1 times r to the power of n minus 1, because this is the n minus first derivative. That's why I have r to the power of n minus 1. And then I keep going up to a n minus 1. And now this is the first derivative. So r would be raised to the power of 1 plus, there is no derivative here, so it will be just a n equal to 0. So I have a lot of students who have trouble with a generalized, like a table to express different scenarios that could rise if n, is maybe 4 or 5 or 6. So I will first summarize these in this table, and then I will give you one example to make sure that everything is synced in. So depending on the roots of r, we will have different possibilities. First of all, depending on what this n is, for example, if the highest order of the derivative is 3, n would be 3, we will always have the same number of roots. So this is an nth order polynomial, so we will expect to have n solutions for this algebraic equation. So let's say you somehow factor this polynomial, and in the factored form of the characteristic equation you have one parenthesis in the form of, let's say, r minus a constant that is a real, like alpha, r minus alpha to the power of 1 times other terms equal to 0. So in this case, this is called a simple root because the exponent of r minus alpha is 1. So r equals alpha is a real simple root. In that case, for the solution of this differential equation, one of the terms would be a constant like c, I call this c1, times exponential of this simple root, in this case alpha, times the independent variable x. In case the multiplicity is larger than 1, meaning the power of r minus alpha is larger than 1, let's say it is r minus alpha to the power of 4 times other terms equal to 0. In this case we call the multiplicity, or m, is equal to 4, while r equals alpha is still the solution. So in this case what we're gonna do is we're gonna have more than just e to the alpha x. While c1 e to the alpha x is still a solution, we will have 3 more independent solutions. So we are gonna write c2 e to the power of alpha x, 1 less than this multiplicity, meaning 3. So you're gonna have plus c3 e to the alpha x and c4 e to the alpha x, and then we are going to add x to the power of 1 less than 4, meaning you're going to have x to the 1, x to the 2, and x to the third, meaning x cubed. Okay, so all of these terms, so as you can see, e to the alpha x is in common, but then we have x squared, x cubed added for each of the terms. So because the multiplicity was 4, if the multiplicity was 5, I would have continued up to x to the 4 times e to the alpha x times c5. Okay? For the complex root, meaning you have a term like r minus alpha plus I beta times other terms equal to 0, this is called a simple complex root because the power of this term is equal to 1. So r equals alpha plus I beta is the solution. So we know from basic algebra that for a polynomial, if alpha plus I beta is the solution, the conjugate of that, meaning alpha minus I beta, is the solution. I'm not going to prove it here, but that is from basic algebra. In that case, you're going to have c1 exponential of the real part is alpha x, times cosine and sine of imaginary, let's say cosine beta x, plus the next term is the same thing but with the sine, so c2 e to the alpha x, but sine of beta x, as two independent solutions related to this complex root. But this was when the multiplicity was 1. What if the multiplicity is more than 1? Meaning it's not a simple root, but we have multiplicity of 2 or more than 2. Let's say you have r minus alpha plus I beta to the power of, let's say, 4, like the previous case, times other terms equal to 0. So in this case, we will treat exact same thing as when we had the real roots. As you saw, we added some extra terms until 1 less than multiplicity. So same concept here. While you would still have the roots of a simple complex root, meaning c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x, but then you have to include x squared and x cubed for each of these terms, meaning c3 times x e to the alpha x cosine beta x plus c4 x times e to the alpha x sine beta x, and then c5 x squared e to the alpha x cosine beta x plus c6 x squared e to the alpha x sine beta x, x should be there. And then since the multiplicity was 4, I have to stop at 3, so we will need 2 more terms. So c7 e to the power of alpha x times x cubed times cosine beta x, and then finally c to the 8 e to the alpha x x cubed sine of beta x, right? And we will stop there. Let's practice this process in one example so we make sure that all these rules are synced in. Let's say we have a 7th order linear differential equations with constant coefficients. So the first step is to write the characteristic equation. It's a very simple 7th order or the seventh derivative of y would be replaced with r to the seventh. This is the sixth derivative, so it would be r to the sixth. We are transferring the same coefficients. The third term here is 4 times fifth derivative, so it will be 4r to the fifth. 3y triple prime would be 3 times r cubed minus 5 times r squared, and there is no derivative here, so we will just have minus 4 equals to 0. So somehow we have to solve this seventh order polynomial. So you may not see this in an exam, but the point here is not to learn how to solve a polynomial, but to learn how to incorporate different terms in the solution of the homogeneous equation. So if you solve this polynomial, if you plug r equals 1, 1 plus 1 plus 4 is 6, plus 3, 9, minus 5 minus 4, it will be 0. It's easy to check. So r equals 1 is for sure a solution, and that means you would have an r minus 1 as one factor term of this equation. If you divide this polynomial by r minus 1 and perform some factorization, you will end up getting r minus 1 times r squared plus 1 times r squared plus r plus 2 quantity squared equals to 0. Once you factor, you will focus on each of the parentheses. The first parenthesis is r minus 1. So if you set that equal to 0, that gives you r equals 1. So it is a real number. There is no imaginary part. And this multiplicity is 1. It's a simple root because the power of the parenthesis is 1. This means that y as a function of x will have a term like a coefficient c1 times e to the power of this simple root, in this case 1, times independent variable x. Now we will go into the second parenthesis. The second parenthesis, if we set that equal to 0, r plus 1 equals to 0, that gives me r squared equals minus 1, or r equals to plus or minus I, imaginary number. So if we compare this with this format of alpha plus I beta, it looks like there is no real part. This means alpha is 0 because it is technically 0 plus or minus 1i. So that means alpha is 0 and beta is 1. So in this format, you would replace alpha with 0, so exponential terms cancel, and we only have cosine and sine of beta. In this case, beta is 1 because this is plus or minus 1i. So the second term and the third term will have cosine, exponential cancels because it is e to the 0, so it's cosine of the coefficient of I, which is 1, cosine of 1x, or just cosine of x, and sine of x. And that would conclude the second parenthesis. Now for the third parenthesis, we have a quadratic, r squared plus r plus 2 equals to 0. You can use quadratic formula, negative b, the coefficient of r, negative 1, plus or minus square root of b squared, which is 1, minus 4 times a times c, divided by 2a. So 1 minus 8 is minus 7. Under the radical comes imaginary number. So you will end up getting negative 1/2 plus or minus I times root 7 over 2. So this means minus 1/2 is our alpha, and root 7 over 2 is the beta in this case. But note that the multiplicity is 2. So not only these two terms would be present, but also since the multiplicity is 2, we have to incorporate up to the first power, because like I said, multiplicity minus 1. In this case, multiplicity was 2, so I have to incorporate x to the 1 for the other term, meaning, let's write C4 times e to the real part minus 1/2 x times cosine of imaginary part root 7 over 2x plus C5 e to the minus 1/2 x times sine of root 7 over 2x plus, okay, now since the multiplicity is 2, I will basically copy these two, and so it would be C6 times e to the minus 1/2 x times x to the 1, because 1 less than the multiplicity is 1, so we have to stop at x to the 1, times cosine of root 7 over 2x plus C7 e to the minus 1/2 x times x times sine root 7 over 2x. And we are done. Note that if this power was 3, we would have continued with the 8th and the 9th term of x squared. But I stopped at 1 because 1 less than 2 is 1, so I stopped there. Note that the number of independent terms in this homogeneous solution is 7. We have 7 terms with 7 coefficients attached, matching the order of the differential equation, in this case 7. So this will conclude this video. Hope you guys enjoyed this video. All I'm asking in return is if you smash the like button and subscribe to my channel for more videos. If you have any questions, feel free to ask in the comment section. Good luck, and I will see you next time.